Okay, so this video is going to replace the discussion on April 1st, Monday, and so this is going to be the last discussion before exam 2. So if you remember before exam 1, we talked about the 3 subjects right before the exam because you don't get a quiz on these 3 subjects, so in place of that you basically see about a quiz's worth of questions on this material on the exam. So wanted to take a discussion to focus on these 3 topics to make sure that you are all ready for the exam on these 3 topics. So we've got the maxes and mins, we've got the mean value theorem, derivatives, and graphs. So we're going to start off with 4.1, which is maxes and mins. The vocabulary to know here is the critical point, where f prime of x equals 0 or doesn't exist. So basically a critical point is just where your derivative either equals 0 or the derivative just doesn't exist. Either one of those are a critical point, and yeah, that's pretty much it. And that plays into the closed interval method, which we are going to talk about in question 1. So if you're feeling pretty confident about your ability to do this problem, use the closed interval method, then I encourage you to pause the video and then go ahead and give it a shot. So you always start closed interval method problems with taking the derivative of your function. So f prime of x, this is going to be 2x minus 4, right? Pretty basic power rule derivative. And then you want to set your derivative equal to 0 because, as we remember, critical points are where f prime of x equals 0 or does not exist. But this is going to exist everywhere, right? Because it's a polynomial. So we just set it equal to 0. So 2x minus 4 equals 0. So then we move that 4 over. 2x plus 4, and we divide both sides by 2. Here, I'll draw that out. So then x equals 2. So now we're looking to find our maxes and mins. So we have 3 possible candidates for maxes and mins. Our first one is our critical point. Our second one is our first endpoint. And then our third one is our second endpoint. So we're going to try all of these, and by try them, I mean plug the x values into the base function. So we're going to plug f of 2, which we got from here, right? That's our critical point. That's a potential max or min, so we're just going to plug it into our base function. So it's going to be 2 squared minus 4 times 2, which is just 4 minus 8, which is negative 4. So then we plug in negative 1, because that's our first endpoint. That's another candidate for a max or a min. So f of negative 1 equals negative 1 squared minus 4 times negative 1. So that's going to be 1 plus 4, because we got that double negative there. So that's just going to be 5. And then finally, our third candidate the max or min is going to be 4 because that's our second endpoint. So then we just plug 4 in, 4 squared minus 4 times 4. 4 squared is 4, 4 times 4 squared is 16, and then 4 times 4 is 16. So that's 16 minus 16, which equals 0. So now we go through, and we need a max, and we need a min. So for the max, we go through, we look at negative 4, we look at 5, and we look at 0. And we say, which one is the largest? Well, 5 is the largest, right? So we say we have a max of 5 at, and then what x value does it occur at? Negative 1, right? So we have a max of 5 at x equals negative 1. For min, we look at the same 3 points. We look at which one has the lowest value, and that's going to be negative 4, right? So we say we have a min of negative 4 at x equals 2. And that's literally it. That's the closed interval method. That's how you go about it. So then if we go to question 2, if you want to give this one a shot, go ahead. Pause the video and then give it a shot. And then our first step is always to take the derivative, right? So we're going to start off with question A here. So the derivative of this is going to be a chain rule where our outside function is negative x cubed. Our inside function is x plus 1. The derivative of x plus 1 is just 1. The derivative of negative x cubed is just going to be negative 3x squared, right? So then, if you remember, our chain rule formula is f prime of g of x times g prime of x. So then we just plug in, so we got negative 3x squared, and then for x, we plug in x plus 1 squared, and we multiply it by 1, because that's our g prime of x. So now that we have our h prime, we want to figure out where it equals 0. So I'm just going to rewrite it real quick. So negative 3x plus 1 squared, and we want to set that equal to 0. We can divide both sides by negative 3, and then we can take the square root of both sides to get x plus 1 equals 0, and then we can subtract that 1, move it over, x equals negative 1. So that's our critical point. So, but you may have noticed, negative 1 is not on this interval. So when that happens, we can't use our critical point as a candidate for max or min. So that means that when our critical point is not on the interval, we only have 2 candidates for maxes and mins. We've got 0 and we've got 1, because those are our 2 endpoints. So if we plug in 0, f of 0 equals negative 0 plus 1 cubed, which is just negative 1, and then plug in 1, sorry, this is h, not f, whoops. So then h of 1 is just going to be negative, and then 1 plus 1 cubed. So that's going to be negative 2 cubed, which is negative 8. So now we look at these two, and we say we have a max of, and then we're looking at negative 1 and negative 8. Figure out which one of those is a higher value. Obviously, negative 1 is a higher value, and then at x equals 0. And then we look at negative 8 and negative 1 again, figure out which one of them has the lower value, and that's going to be negative 8. So we have a minimum of negative 8 at x equals, and then what x value does occur at? Well, that occurs at x equals 1. Okay, so that's how we would go about that. I'm going to bring b down here. So if you'll notice, the only difference with b, the function is still the same, but we have 2 different endpoints, right? And again, the endpoints are always candidates for maxes and mins. So, but this also now includes this x equals negative 1 for the possible maxes and mins. And that's because the interval, or x equals negative 1, right? Negative 1 is between negative 2 and 2. So then now we actually use it. So we just plug in f of negative 2, and that's just going to be equal to negative 2 plus 1 cubed, which is negative 1 cubed, which is just 1. Then we plug in regular 2. We get negative 2 plus 1 cubed, and that's going to be negative 3 cubed, which is negative 27, right? Because 3 times 3 times 3 is 27. So we've got 1, we've got negative 27, and then now we also plug in x equals negative 1. It looks like it's saying negative 13, but it is not. That's just our third candidate for our critical points. So f of negative 1, that's just going to be negative 1 plus 1 cubed. That's going to be negative 0 cubed, and as we all know, that's just going to be 0. So then now we say we got a max. So we get a max of, and then we look through which one has the highest value. That's going to be 1. So 1 is our highest value. That's going to be our max on the interval. Max of 1 at, and then the x value that it occurs at, well, that's going to be negative 2. And then we're looking for our min of, and then what's our lowest value here? Well, that's going to be negative 27, right? By like a mile at x equals, and then 2. At x equals 2. So that's how you do the closed interval method. If you have any questions about this, feel free to email me. All right, so 4.2 is the next unit that we're going to be talking about, and it's really just the mean value theorem and its Rolle's theorem, and they're both very similar. Rolle's is just like a specific thing of MVT. I'll explain all that in a second. So, but just starting with the mean value theorem, you have two conditions that you need to specify first. You have to be continuous on the closed interval a to b and differentiable on the open interval a to b. These MVT problems can pop up a lot in multiple choice sections and stuff like that. Just knowing the definition of the MVT is usually a really good thing to know ahead of the exam. So basically, if you're continuous on the closed interval and you're differentiable on the open interval, then there's some point on the open interval where f prime of c equals f of b minus f of a over b minus a. So that's a lot of words and that's a lot to remember. So let's just break it down. So first of all, this is, if you remember, this is the average rate of change formula that, you know, it's like it goes all the way back to like algebra or pre-algebra even, you know what I mean? This is like the distance between, or this is the average slope between two points, right? So that's all this is really saying is, so I always like to draw this picture. So imagine you have a truck that's going from Baltimore to Washington, and Baltimore and Washington are like, what, 40 miles apart, something like that? So then say that the truck makes it there in 40 minutes. So if the truck makes it 40 miles in 40 minutes, then we know that the truck is going 60 miles an hour, right? Or sorry, it went 60 miles in 60 minutes. So, or sorry, it went 40 miles in 40 minutes. So the average speed of the truck during those 40 minutes and those 40 miles, right, is 60 miles an hour. Because, you know, 60 miles an hour is 1 mile per minute. So we know the average speed that of the truck between the two cities is 60 miles an hour. The mean value theorem lets us say that we know that the truck was going 60 miles an hour at least some point in there. So if this is like, if this is miles per hour and then this is time, and say this is 60 miles an hour, right? The truck, you know, maybe it was going really slow and then it popped up and then, you know, started going 80 or something like that. It could have done that. It could have done the opposite. You know, it could have stayed at 60 the whole time, right? It could have done this because, you know, it hit traffic lights or whatever. But all the mean value theorem is saying is that somewhere between the beginning and the end of our interval, it hit 60 miles an hour at some point because that's the average rate of change on the interval. So that's how I like to conceptualize it. So now looking back at our definition, all it's saying is this is the average rate of change between A and B, right? That's like, this is the average slope between A and B. So all it's saying is that at some point it hits its average slope. You know what I mean? At some point the actual slope equals the average slope. You know what I mean? So that's the mean value theorem. That's all it really says. It can be, once you get your head around it, you know, it kind of makes a lot more sense. But, you know, it is kind of an overload of information at the beginning. But once you, like, it melds, you know, that it's like, okay, at some point the average rate of change equals the actual rate of change, then it's like, okay, you know, and everything starts to fall into place. So Rolle's theorem is very similar to the mean value theorem. Actually, it's literally just the mean value theorem, but with an added stipulation that f of a equals b. So I always like to think about for this one, like if we have the graph y equals x squared, right? And it looks something like this. And like, what if we use the mean value theorem on these 2 points, like f of -2, that equals 4, and then f of +2 equals 4. Like, if we were to use the mean value theorem on these 2 points of the same graph, right, you would draw your average rate of change. Your average rate of change between these two is going to be equal to 0, right? Because if you're reaching the same y value, like it's just a horizontal line. You know what I mean? The average rate of change is a horizontal line, so it's equal to 0. The average rate of change between those two equals 0. So, and that's basically Rolle's theorem. That's literally Rolle's theorem. So Rolle's theorem basically says, right, for the purposes of this, that the graph flattens out because these two y values are the same. So Rolle's theorem says that the graph has to flatten out between somewhere between -2 and 2. And Rolle's theorem is totally right. It does at 0. You see what I'm saying? So it's like Rolle's theorem is literally just the mean value theorem, but with this extra stipulation. So f is still got to be continuous on the closed interval, and it's still got to be differentiable on the open interval. And then f of a has to equal f of b, and then f prime of c equals 0. But that makes sense, right? Because like if f of a equals f of b, then like it equals 0. Because if f of b equals f of a, then f of a minus f of b equals 0. So then this whole thing, this whole average rate of change thing, will always equal 0, right? Because the numerator is always going to be equal to 0. So then the whole thing's always going to be equal to 0. You know what I mean? Like, it doesn't matter what b and a are. If your numerator is 0, the whole thing's going to be equal to 0. So that's where we get Rolle's theorem. Rolle's theorem is literally just the mean value theorem, but where f of a equals f of b. And since f of a equals f of b, then we get 0 for f prime of c, instead of like the average rate of change. So a problem, and so, you know, mean value theorem and Rolle's theorem are, you know, very common on the multiple choice or the true or false section. But there's also some, like, you could be asked like this kind of question on like extended response or whatever. So suppose we know f prime of x is between 1 and 4, and f of 0 equals 3, so we want to find a range of values for f of 2. So basically, the mean value theorem, so the first step is to say that we can use the mean value theorem. And how do we do that? Well, f of x is continuous on 1 to 4. F of x is differentiable on 1 to 4. So then f prime of c equals f of b minus f of a over b minus a for some c on the open interval a to b. So it's always good to start by just, you know, stating your mean value theorem. So now that we've established that, we can actually plug in this for f of x. So we can say 1 is less than or equal to, and then is less than or equal to 4. And then in the middle here, we're going to put f of b minus f of a over b minus a. Because, right, all mean value theorem is stating is that f prime of c equals this for some c, right? So we just literally substitute it in, and then we go and we pick our value. So this is going to be our b, 0 is going to be our b, right? 3 is going to be our f of b, 2 is going to be our a. Actually, here, since it doesn't really matter, let's just make 0 our a, or sorry, 0 our b, and then 2 our a. Is that what I had the first time? I can't remember. So you can do either one. It really doesn't matter what order you put them in, but this way will, I think, work out a little bit better. So our f of b is 3. Our f of a we don't know yet. That's what we're trying to figure out, right? We're trying to figure out a range of values for f of a. Sorry, it's not f of a, right? It's f of 2, because that's our value for a that we're talking about. And then our b is 0, and then our a is 2. So then that's less than or equal to 4. So now we just do a little bit of algebra. 1 is less than or equal to 3 minus f of 2, all divided by -2, right? And then 4. So then we can multiply everything by -2, right, to get rid of that denominator. So we got -2, and then remember, when we multiply inequalities by a negative number, we flip the sign of the inequalities. So then this would be -8, right? Yeah. So then we want to isolate this f of 2 in the middle, so we're going to minus 3 from both sides. So it's going to be negative 5 and negative 11, respectively. And then we're going to divide by negative 1 again. So it's going to be 5, and then the signs are going to flip again, right? So then we know f of 2 is somewhere between 5 and 11, right? And that's how we would go about solving that problem. And feel free to email me if you have any questions. All right, and the last unit that we're going to talk about today is going to be derivatives and graphs. So we've really got two sets of things that we need to know, some stuff for the first derivative and some stuff for the second derivative. I'll put it all here on one screen for you if you want to take a look at it, write it down, try and remember it. It's all stuff that you could more or less be responsible for knowing, and yeah, it's kind of a lot, and so let's just get into an example and see how we would apply this knowledge. So we're looking for the maxes, mins, intervals of increasing, decreasing, inflection points, and intervals of concave up and down for f of x equals x cubed minus 3x squared minus 9x plus 4. So, right, we've got stuff that we can learn about our function from the first derivative and the second derivative. So we'll do the first derivative in yellow and then the second derivative in blue. So first thing, in order to find out information using our first derivative, we got to find the first derivative. So we got to take the derivative of our f of x, and so we're going to get something like this. And so now, we're going to set it equal to 0. So 3x squared minus 6x minus 9 equals 0. And now, so this is a factoring situation, right? We want to factor it. So, or actually, before we factor it, let's factor out a 3. Make it a little easier. And however you know how to factor is fine. It's a skill that, that is presumed to have, carried over from pre-calc or whatever. So this would be a good time to bone up on it, and, in case you're a little rusty on it, which would make sense. So this is how I factor. So then this is going to factor to x minus 3, and then x plus 1 equals 0. And remember, this is still our first derivative, right? So what makes this 0? Well, that's going to be where x equals negative 1 or x equals 3. So those are going to be our two zeros for our first derivative. And if we look back here, well, equals 0, that's a critical point. So we can label these critical points. And then another thing that up there says is, if we go from increasing to decreasing, right, where our first derivative is positive, we're decreasing, where our first derivative is positive, we're increasing, and then where our first derivative is negative, we're decreasing. So let's make a little sign chart where we've got negative 1 over here and then 3 over here. And then we can plug in, let's plug in a value between the two. So we'll plug in 0, and what is that going to give us? So if we plug in 0 here, so this is going to give us negative 3, and then positive 1, which is going to give us a negative 3. So that's going to be negative, so we know we're negative on that interval. And then you could plug in negative 2, and then that would give you positive, right? Because this would be negative and this would be negative. Double negative is a positive. And then over here, if you plug in, say, like 4, right? This term would be positive and this term would be positive. So we really only care about the sign of the term. And so that's going to be positive from negative infinity up to 1, negative from negative 1 to 3, and then positive from 3 to infinity. So then we can take that and we can say we are increasing from negative infinity to negative 1, and then again from 3 to infinity, because that's where our first derivative, right, is positive. And then we are decreasing from negative 1 to 3, because that's where our first derivative is negative. And then so now we also have maxes and mins. So maxes and mins, probably, or at least a little familiar with it from 4.2. But so whenever we go from increasing to decreasing, we have a local max. So we have a local, sorry, let's just say local max at x equals -1, and then we have a local min at x equals 3. So we have a local max because we go from increasing to decreasing at -1, and then we have a min because we go from decreasing to increasing at 3. So that's why we have our local max and our local mins. You could plug this x value into f of x, regular f of x, to get the value of our maxes and our mins, but for the sake of time, I'm not going to be doing that. So then we've extracted all the information we can from our first derivative, right? We got our maxes, we got our mins, we got our intervals of increasing and decreasing. Now everything else is going to come from our second derivative test. So let's find our second derivative before we do anything else. So we're just going to take the derivative of our first derivative, and that'll give us our second derivative. So it's going to be 6x minus 6, right? That's our second derivative, and right away I'm going to want to factor out a 6. It's going to make it a lot easier because we're going to have to find the zeros of this too. So we're going to set 6 times x minus 1 equal to 0, and we're going to divide it by 6, so x minus 1 equals 0. Add a 1 to both sides, we get x equals 1. That's going to be our 0. So we're going to make a sign chart with that. It's pretty much the exact same way as we did with our first derivative, right? It's just a little bit easier because we don't have to factor anything when we've only got one point. And so to the left, so let's say we plug in 0, right? If we plug in 0, we get a negative here, and then that 6 is always positive, so that's going to be negative. And then if we plug in, I don't know, say we plug in 2, that's going to be 6 times 1, which is positive. So that's going to be going from negative to a positive. So, and if we remember, when we switch from positive to negative or negative to positive, we have an inflection point. So we have an inflection point at x equals 1. And so now, the only, like how we had our intervals of increasing and decreasing here, we also have intervals of concave up and concave down that we need to figure out. So let's go ahead and mark off our inflection points. All right, so now we are concave down where our second derivative is negative, right? Think about it, negative down, makes sense, right? So that's going to be from negative infinity all the way up to 1. And then we're going to be concave up where our second derivative is positive, and that's going to be from 1 up until infinity, right? So from 1 to infinity, we're concave down. From negative infinity to 1, or sorry, from negative infinity to 1, we're concave down. From 1 to infinity, we're concave up. And so that finishes our checklist. And so, now we have used our first and our second derivative test to figure out all the information that we can about that function. So that would be complete. And I guess one other important thing to know, might be important, is if your first derivative equals 0 and your second derivative is greater than 0, it's a local min. If double prime is less than 0, local max. That's something that you could be responsible for knowing, I'm not sure. So basically, like, one way we figure out that we have a local max or a local min is by, seeing where the sign changes and stuff. But you could also do it with your second derivative, like for example, at -1, right? So we know we have a 0, or we have a critical point at x equals -1, right? So, but if we don't know if that critical point is a local max or a local min, we can plug it into our f double prime of x. And so when we plug in -1 here, we get 6 times -2, so that's -12. So that tells us, and our first derivative is 0, and our second derivative is negative, so that means we have a local max at -1. So that's an alternative way we can do that. Okay, so now maxes, mins, intervals increasing, decreasing, inflection points, intervals concave up, down for f of x equals ln of x squared plus 5. So similarly to the last problem, we're going to start with our first derivative, and we're going to start just by taking the derivative. And this is going to be a chain rule problem where our outside function is going to be ln of x. Our inside function is going to be x squared plus 5. Derivative of ln x is just 1 over x. And the derivative of x squared plus 5 is going to be 2x. So, and then remember our chain rule formula is f prime of g of x times g prime of x. So then that's 1 over x squared plus 5 times 2x, which we can write as 2x over x squared plus 5. So now this is our first derivative, so now we want to set it equal to 0. So 2x over x squared plus 5 equals 0. So, well, we know that if we plug in 0, it'll make it 0. So we have a critical point at 0. Well, so here, let's just divide both sides by 2. Come on, erase. Okay, so if we divide both sides by 2, we get x over x squared plus 5 equals 0. And so we can tell that we have a critical point at x equals 0. Because if we plug in 0, it makes the whole thing 0. So, all right, so that's how we found our critical point. So then we just make a sign chart. So we got it 0. And then we plug in -1. Let's plug in -1, see what we get into our f prime of x. So that's going to be this, and we get negative, and then this is always going to be positive because, like, you square a -1, it becomes +1. You square anything negative, right, it becomes positive. So the denominator is always going to be positive, and this numerator will be negative. So we're going to have a negative there. And then if we plug in +1, right, this is going to be positive, and then this is also going to be positive. So we're going to go from negative to positive there. So that means, since we're talking about our first derivative, that means we're going to be increasing on the interval 0 to infinity, because that's where our first derivative is positive. We're going to be decreasing from -infinity up to 0, because that's where our first derivative is negative. And so then that means we have a local min at x equals 0, and we do not have a local max. Okay, so now for our second derivative test, we are going to take the derivative of this. So f double prime of x equals, and this is going to be a quotient rule. So where our, right, if it's u over v, or however you know your quotient rule, u equals 2x, and then v equals x squared plus 5. The derivative of 2x is just 2, and the derivative of x squared plus 5 is just 2x. And so then it follows the form u prime v minus uv prime over v squared. So then we've got 2 times x squared plus 5 minus 2x, and then 2x. Is that right? 2x and 2x? Yeah, that's right. That's just kind of interesting. So then that's 2x squared plus 10 minus 4x squared all over v squared, and v is going to be x squared plus 5, so that's going to be x squared plus 5 all squared. So this is going to be our f double prime of x, and we can simplify this a little bit, right, because we can combine those x squared terms. So it's going to be negative 2x squared plus 10 divided by x squared plus 5 all squared. All right, so now we got to figure out the zeros for this. So if you notice, the denominator is always going to be positive, right? Like anytime you would put in a negative, it would just get squared, and that negative would immediately go away. You know what I mean? So there's no chance for this denominator to ever be anything other than positive. It's always going to be positive. So that means we really only care about the numerator. So we're just going to set the numerator equal to 0. Actually, let's just set the whole thing equal to 0 and just worry about the numerator. Okay, so then we can factor the top. So we can factor out a -2, x squared minus 5 over x squared plus 5. And then now we can say, okay, this equals 0. We can set this equal to 0, right? The x squared minus 5, set it equal to 0. Add 5. X squared equals 5. So x equals plus or minus the square root of 5. That is when our x is going to be equal to 0. So then our sign chart for our second derivative will look like this. And then, because remember when you square or take the square, like it's plus or minus. Wait, that's not true, is it? Wait, Yeah, oh yeah, it is true. It is true, because when we take the square root of this, it becomes plus or minus. All right, yeah, so it's plus or minus the square root of 5. So then we plug in something to the left of negative square root 5, and we get, so what's something to the left? So negative square root 5, that's like a little more than 2. That's like a little more than 2, so let's plug in -3. If we plug in -3 to this, that's 9 minus 5 times -2, so that's going to be negative, and our denominator is always positive. If we plug in something in between here, so say we plug in 0, right? This term is negative because it's 0 minus 5, but that gets multiplied by -2, so that makes it positive, and then the denominator is always positive. So it's going to be like that, and then this is also this interval is going to be negative for similar reasons to this. So, okay, so now we can say, okay, we are concave down on the interval -∞ up to negative square root 5. And then again from square root 5 to infinity, right? Because that's where our second derivative is negative. And then we are concave up where our second derivative is positive. So that's going to be from negative square root 5 to square root 5. And then we have inflection point where we go from either positive to negative or negative to positive. And if you notice, we do it here at -5, and then we also do it again here at positive square root 5. So x equals negative square root 5 and positive square root 5. So there we go. We've got concave down, concave up, inflection points, increasing, decreasing, local max, and local min. So we are all finished here. You can feel free to email me if you have any questions, and yeah.